So Born Haber cycle uses Hess's law to calculate the lattice enthalpy, which is something we can't really measure experimentally very well. So let me explain to you the difference between lattice enthalpy and enthalpy of formation. Okay, I haven't got any deltas, so I'm just going to write delta HF. That's the enthalpy of formation. Okay, so that is the enthalpy change for formation of the solid ionic compound. I can't spell ionic compound from its constituent species in their standard states, okay? From elements in standard states, which, as you know, standard state will be like, usually is like 25 degrees Celsius, 1 atmosphere pressure, blah, 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 blah. The lattice energy, which we're just going to call delta H lat, but lattice energy, again, is the formation of a solid ionic compound, okay? Just going to copy and paste, but it's from its gaseous ions, okay? So just think about that. Like if we were forming sodium chloride, the difference between the delta H of formation is going to be delta H of formation is from solid sodium, right? Because that's the standard state of sodium at room temperature and pressure, and chlorine gas, which is a homonuclear diatomic gas, versus if we were writing an expression for the lattice energy, that would be forming solid sodium chloride from the gaseous sodium plus cation and the gaseous chloride Cl minus anion. So those are two different things, okay? So when you look at this Born Haber cycle, and in this case, this is just like an energy configuration diagram. You'd have to actually read the energies for each step off here. We can identify the enthalpy of formation, and I'm also going to use an arrow to show the direction of that reaction, that this would be the metal in its standard state and the non-metal in its standard state forming that ionic compound, right? So this arrow from here to here is representing the enthalpy of formation, and we know for energy, right, that positive and negative means something. So if the products are at a lower energy than the reactants, that means energy has been released. So that's going to have a negative sign for the energy release. And if I try and read this off the scale, it looks like it's minus 200 kilojoules are released. Okay. So I now have, from the graph, worked out my enthalpy of formation of going from my elements in their standard states to the solid ionic compound, okay? So the thing we don't know is the lattice enthalpy, okay? The lattice enthalpy is defined as forming the solid ionic compound from its ions in the gaseous state, and it should, again, be a big release of energy. It should be bigger than the enthalpy of formation, because guess what? Gaseous ions are really reactive, okay? So going from here to here is our enthalpy, our lattice enthalpy, and we don't know what that is. So usually this is what you're trying to work out with a Born Haber cycle. Now for this ALEKS question, it's kind of like a gentle introduction for two reasons. Like, first of all, you're not really having to worry about stoichiometry and stuff because that's all been balanced for you. So quite often at the upper level when you do this kind of thing, you will be just told work out the lattice enthalpy for the formation of sodium chloride. And you'd have to look up the enthalpy of formation, the enthalpy of sublimation of sodium, etc., and A, construct this yourself, and B, realize things like going from Cl2 to just chlorine, you need the bond energy for like how much it costs to break that bond. But in the balanced equation, there's only half a mole of chlorine for every 1 mole of sodium, so you'd actually have to divide that number by 2. In ALEKS, you're just going to read it off the scale. But I'm going to be really pedantic and say, hey, it's half the bonding energy or something, because I need to write what it actually is that we're reading off the scale. But for you, you're just looking at the numbers. Also for ALEKS, because there actually is an axis on this scale, you can read off the lattice enthalpy right now, right? So reactants is the cation and the anion, sitting up here at 950 kilojoules, and the product is down here at minus 200. So 950 to minus 200, I'm going to expect my answer to be minus 1,150 kilojoules, right? Because that is the length of that line. Okay, so first of all, let's work out all our processes here, and I'm going to tell you what they all are. You've really got to look at the state symbols and the charges to work out what's changing between reactants and products for each step. So going from here, we can see the metals going from the solid to the gas. Nothing else is changing. So that is the enthalpy of sublimation for our metal, okay? And I'm going to read that off the scale. Look at the direction the arrow is going. The reactants are at a lower energy level than the products, so energy is being absorbed for this transition to happen. So that is costing energy, and it's costing plus 250 kilojoules that I can read off there. Okay, so then the next step, what is changing is that our X2 molecule is being broken asunder. So that would be my bonding energy, okay? But I'm going to be really pedantic and say it's half the bonding energy just because of the stoichiometry there. So that's going from 250 up to 600. So that is plus 350 kilojoules that is costing. Okay, then the next thing was going from the metal gas to the cation gaseous. Okay, so that is the ionization energy of the metal. Okay, in this case, it's just the first ionization energy. Okay, in ALEKS, sometimes it will actually combine the first and second ionization energy into one step. If you were constructing this yourself, you'd have to look up the first and second, maybe even third ionization energy in a table, and you'd have to actually list them all separately. Okay, so this is ionization energy 1 in this case, and that is going from 600 to 1150, so it's 550. I hope I'm adding these up right. Kilojoules that is being absorbed. Now, electron affinities are usually negative. It usually releases energy to gain one or more electrons and form an anion. Very, very energetically favorable. And we can see that because look at the direction of this arrow. The reactants are at a higher energy level than the products, so energy is being released. How much, you say? 200 kilojoules. So that is got a minus sign. Make sure you're careful with your sign. So that is the enthalpy of the electron affinity, and it's just forming a -1 anion, so that's just electron affinity 1. So that's minus 200 kilojoules. So how to get the lattice enthalpy. Okay, I'm going to show you 2 ways. Okay, so way number 1, Hess's law tells us to get from point A to point B. Okay, so this is for the enthalpy of formation. Doesn't matter which route you go because enthalpy is a state function. Okay, so as long as you do the final enthalpy minus the initial enthalpy, right, you're going to get the same thing, right? It's a state function. Therefore, doesn't matter the route you take. So you can either go from A to B. Let me just do some colors here. You can either go from A to B direct like this, and that is your enthalpy of formation, right? Or you could go from A to B all around the houses. So you could go from A all the way to B like this, okay? So we can write an equation for that, okay? You can write that the standard enthalpy of formation is equal to the sum of all these steps going around the other way. So that's your enthalpy of sublimation plus your binding energy, what's it, HBE, plus your ionization energy 1, plus your electron affinity 1, plus your lattice energy, right? We don't know the lattice energy, but we know everything else. So then we would just rearrange and solve for lattice energy. I'm trying to fit this in here, right? So I could just take this and rearrange and solve for lattice energy, make lattice energy the subject of the equation. So I'm going to keep that on one side, and then delta HF is going to be on the other side, right? And then just subtract from that all the other things. So minus all these things. If I've rearranged that correctly, you'll get something a little bit like this. Okay, are we happy with that mathematically? All right, then I can just stick in the numbers. So delta H of formation, be careful because look, it's minus 200. Okay, then minus H of sublimation, minus 250. Then half of our bonding energy is minus 350, minus ionization energy 1. It's 550 minus my electron affinity, but be careful, the electron affinity is negative, okay? So don't screw that up, okay? Remember, our enthalpy of formation was negative and our electron affinity is negative, and a minus gives you a plus. So remember, we were predicting from reading off the graph that this should be like minus 1,150. So let's just check that. Minus 200, minus 250, minus 350. Let's hope I've read everything off here correct, plus 200 gives me, hang on, that's gone wrong, minus 970. Maybe I can't use a calculator. Let me just check and see what I've done wrong. Okay, I must have pressed the funny button on my calculator because it is minus 1,150. I just can't use a calculator apparently. That's got a sticky button too. I don't know why. Okay, so this is method number 1. Okay, so just numerically write an expression for your enthalpy of formation that is equal to all the other processes and rearranging and solving for the lattice enthalpy, because that's the only one you don't know. An alternative way of doing it, which you may have been shown before by somebody, I don't know who, is setting your A and B. Where my text? I'm going to make this light bright pink. Okay, so A to B will define your lattice energy. Okay, so what is the route to get to your lattice energy? Well, it's going to be going all around the houses. Okay, but it's going to be going this way. So look at the direction of those arrows. And the key is, if I am traveling in the opposite direction to the process, which is defined like this, then I have to change the sign. Okay, so the sign of this minus 200 kilojoules is defined for this gray arrow. Okay, so if I've gone the wrong way along the arrow, then I have to change the sign. So what this would look like then is, I'm just going to write delta H of my lattice straight away. So that would be reversing the sign. So I'm going to put minus to say I'm reversing the sign of HE1. Okay, and then let's look, we're going the wrong way along the ionization energy 1. So ionization energy 1 is also minus. Okay, I'm going the wrong way along the sign of the binding energy. Okay, so again, that gets a minus. Okay, and then I'm going to go the wrong way along that grey arrow for my sublimation energy. So again, I'm going to change the sign on that. But I am going the right way along the sign for my enthalpy of formation. Okay. So we literally have just graphically derived the same equation that we got from rearranging Hess's law up here. So if I was going to substitute it in, so minus means I change the sign of my electron affinity 1. So instead of minus 200 kilojoules, it's going to be plus 200 kilojoules. Okay, I'm changing the sign of my ionization 1. Instead of plus 550, it's going to be minus 550. Changing the sign of my bonding energy, so it's going to be minus 350. Changing the sign of my enthalpy of sublimation, so that's going to be minus 250. I'm not changing the sign of my delta H, but it was already minus 200. So I should end up with the same thing if I do 200 minus 550. Whoopsie, that's the problem. I pressed the divide sign for something. That's why it went wrong before. Minus 350, minus 250, minus 200 will give me minus 1,150. And don't forget, you can also read it off the bloody axis as well. Okay, so 2 methods to work out the same thing. Good, I'm glad we're happy. All right, so let's actually look at the ALEKS question. I can't fit it on the screen, right? So I'm going to just scooch down a minute just to look at the question. So it's going to ask us what the lattice enthalpy is, what the formation enthalpy is, right? You can actually read it off the plot, right? But then it has like the fun factor question, right? To make sure we're understanding how to actually interpret energy diagram like this. So suppose the XX bond enthalpy was smaller, so that's the XX bond, and the ionization energy of M was bigger. Would our MX product be more stable or less stable? So first of all, let me show you a couple of things. So on this energy diagram here, wherever this product is right here, it's at minus 200 kilojoules per mole. The more negative that is, like the more stable it's going to be, right? Because it's going to be lower energy. So if that MX moves this way, that is going to be more stable. And if the MX moves the other way, that is going to be less stable, okay? So you have to kind of work through and see if this line position changes if you change one of the other things, okay? So let's scooch back. It was said if the XX bond enthalpy was smaller. So I'm just going to like do a sort of theoretical thing of like, hey, if it was smaller, what would happen? I'll pick purple for that. So if this XX bond enthalpy was smaller, instead of being here, let's say this line was here, okay? But all the rest of the things stay the same. So then that'd be plus 550, minus 200, and minus 1150. If it was just that XX energy was smaller, if I followed that all the way round, I would see that that would actually stabilize my compound because this MX line would move down. However, we were asked about something else changing as well. And the ionization energy was bigger. Ooh. Okay, so the trouble is that ionization energy, if that was bigger, it depends how much bigger it was, right? So if it stayed the same, right, my line would be like here, right, for if that was plus 550. But if it got bigger, how much bigger did it get? It's actually going to depend, right? Because if it got bigger by anything up to this amount, it's not going to change this line. This is going to stay the same. This is going to stay the same. But if it got a lot bigger, okay, so much so that it pushed this line up, then if the electron affinity stayed the same, it'd be here. Therefore, the lattice enthalpy would be here. So actually, this is one of the examples which is impossible to tell without more information. Okay, so I'm just going to get rid of most of this stuff now just to show you a few more examples of just that bit, because I think that is the bit that most people struggle with on this, especially because you've got the scale you can read off the lattice energy, etc. All right, so let's see, less stable. Okay, so let's just work a couple of these through. I'm just going to actually generate a new problem just to get different options down there. So let's see. Suppose both the heat of sublimation and the ionization enthalpy were bigger. Okay, heat of sublimation and ionization enthalpy. So I'm trying not to forget. Okay, so heat of sublimation is this, going from the solid to gas. Okay, so let's just imagine that that was bigger by a little bit. And the ionization enthalpy, which is this one. Okay, so this line has moved from, let's make this purple, from here to here. Okay, so that is bigger. Okay, which would mean this line would also move up, okay, by the same amount, okay, from here to here, okay. Now, if the ionization energy was the same, then this line would move to like here, right? But it was also saying, hey, what if the ionization energy got bigger as well? So say the ionization got bigger on top of that, that's then going to move this line to here, which means this line is, if this arrow stays the same, is about here, and then this would be up here somewhere. So that would correspond to being less stable, okay? Okay, so you just got to kind of work it through. So I find it useful to sort of imagine moving the line up by like a certain amount. And remember that will go all the way round, that each line will be moved up or down, assuming everything else stays the same. So you've got to work out if the two values they ask you about are working in harmony of each other to move your lattice energy in one direction or the other, or if they're working against each other. And whenever they're working against each other, you can't tell because it's going to depend on their relative magnitudes.